So the title of my talk is Length of Frame Bicategories. My name is Orendain. I'm a postdoc at the National University of Mexico, UNAM. So the program that I'm going to be talking about today stemmed from the following problem posed by Bob Perret in Personal Communication. So the problem asks to define sensible numerical invariance for double categories. Yeah, this is stated in somewhat vague terms, but it's a very interesting problem or question. So related to this is the following question. What are the simplest squares in a double category? So this is even more vague and obviously depends on who you ask and who answers. But my answer to this will lead to a partial solution to the problem above. So first, we'll observe that bicategories can be identified with vertically discrete double categories. So this is the classic embedding of bicategories into double categories. Now, assume for a minute that we know everything we need to know about bicategories. Of course, bicategories are very difficult objects, but just for now, assume that we know everything about them, that for us they're trivial. Now observe that if we know bicategories, then we know categories. So we know everything we need to know about both bicategories and categories. Now if C is a double category, then if we know bicategories, then we know the horizontal bicategory HC of C, and we know the category of object C0 of C. With this assumption that we know everything we need to know about bicategories, we can have an answer to this question of what are the simplest possible squares in a double category. The simplest squares in a double category are the ones that we know everything about. So globular squares, which are the ones corresponding to the horizontal bicategory of C, and horizontal identities, which are the ones corresponding to the category of object C0 of C. Okay, well, with this assumption here, I will define numerical invariance for general double categories. I'll start by defining numerical invariance to certain squares in general double categories. So suppose C is a double category, let phi be a square in C. Then we'll say that phi is of complexity 0 if we know everything we need to know about phi. If phi is one of those simplest possible squares in C, that is. We'll say that phi is square of complexity 0 if phi is either a globular square or a horizontal identity square in C. So we draw squares of complexity 0 in our double category C like thus. Now consider squares in C that can be subdivided as a vertical composition of squares of complexity 0. That is, consider squares that look like this, that can be written as a vertical composition of squares marked by 0. So we say that squares that look like this and are not of complexity 0 are of complexity 1. So squares of complexity 1 are vertical compositions of squares of complexity 0 that are not of complexity 0. And we picture these squares like thus. Now suppose we're given squares phi and psi of complexity 0 such that the horizontal composition of phi and psi is defined. Then it can be the case that we can find vertical subdivisions of phi and psi into squares of complexity 0 that look like this. That is, that the squares of complexity 0 match horizontally. So in that case, we can compose all the squares of complexity 0 horizontally and then compose the whole thing vertically. And then we would obtain a vertical decomposition of the horizontal composition of phi and psi into squares of complexity 0. And then in that case, this horizontal composition would be of complexity at least 1. But it can also be the case that for every complexity 0 vertical subdivision of these squares phi and psi, the horizontal composition looks like this. The complexity 0 squares do not match horizontally. Then in that case, the horizontal composition of phi and psi is not of complexity 0, nor is it of complexity 1. So in that case, we'll say that this square is of complexity 1 plus 1/2. So more generally, the square of phi in our double category C is of complexity 1 plus 1/2. If phi is not of complexity 0, it's not of complexity 1, and phi admits a horizontal subdivision like so into squares of complexity 1. So we draw squares of complexity 1 plus 1/2 like this. Now we can run this process inductively. So n is a positive integer. Suppose we have defined squares of complexity less than n. Now squares of complexity 0 are squares not of complexity less than n, admitting a vertical subdivision, like so. Okay, so that defines squares of complexity n. Now squares of complexity n plus 1/2 are squares not of complexity less than n plus 1/2, admitting a horizontal subdivision, like so. So we picture squares of complexity n plus 1/2 like this. So now we can define inductively complexity, arbitrarily large complexity of squares. Now we have a warning here, a very important warning. Not every square in a double category has a complexity. If it does have a complexity, then we say it's globularly generated. The square is globularly generated or has complexity if it can be subdivided into globular and horizontal identity squares. But not every square in a double category satisfies this condition. So a double category C is globularly generated if every square C has complexity, or equivalently, if every square in C is globularly generated. If C is a general double category, not necessarily globularly generated, then the collection of squares in C that are globularly generated is a sub-double category of C. We write this as gamma C. Gamma C satisfies these two equations here. We call gamma C the globularly generated piece of C. Now, why do we care about this globularly generated piece? Well, we have this complexity for some squares, for globularly generated squares of a double category. We have a general double category, then we can't pick a square and compute its complexity, but we can compute its globularly generated piece, which here says that it's the base of Grothendieck fibration. And then in that base, we can actually pick any square and we can compute its complexity. Okay, so we have the following definition. Suppose C is a double category, then the vertical length of C, LC, or just the length of C, is the floor of the supremum of all complexities of squares in gamma C. So this is an invariant for double categories, a numerical invariant. So this answers Bob Perez question. So, well, if it's sensible or not, we'll see. But well, what can we compute with this, or what can we say about this invariant? Well, first, the length of all these double categories here, the double category of bimodules, the double category of profunctors, the double category of Bordisms, the homotopy double grouphood of a topological space, or the double category of polynomial comonoids, they're all have length 1. So we have the natural question, are there double categories with length different than 1? The answer is yes. There exists a sequence of double categories with length n for every n. And we can actually take the limit, and the limit has a length infinity. So, well, there's something in common with all these double categories. They're all frame bicategories. So we have the following conjecture. If C is a frame bicategory, then the length of C is 1. So this is the title of the talk. And this is a conjecture, but yeah, this is not published yet, but this is already proven. So yeah, we can think of this as a theorem, but I think we have to wait a couple of weeks or maybe months for this to actually become a theorem. But well, so length of frame bicategories is 1. We have the related question of Pronk. So are there double categories that have length 1 but are not frame bicategories? And the answer is yes. No non-trivial globularly generated double category is actually a frame bicategory. So if we have a frame bicategory, then this has length 1, and its globularly generated piece also has length 1, but it's not globularly generated double category. So every frame bicategory contains a double category that is not a frame bicategory and has length 1. So you have the following question: are there globularly generated double categories of length 1, but that are not the globularly generated piece of a frame bicategory? And the answer is yes. So this was a very nice question of Pronk that was solved in the past week. So yeah, there's lots of very interesting questions about this invariant, and hopefully we'll keep working on this. And if anyone's interested in this, please write me an email, and I'd be very happy to talk about this. So thank you very much.